Good morning. So I was planning today, and I still will, talk about some completely different work, which is also joint with Ben Morris. So today will be somewhat Ben Morris day, but I'll do that in the afternoon. And this morning, I want to talk about some progress towards the characterization of cutoff, the cutoff phenomenon, which I'll remind or define for you a little later. But before getting into that, I want to just state what is kind of the key tool that's, or a key tool that's used in this work, which is resultant about Markov operators from the 1960s, which hasn't really been used by kind of our mixing community until recently. So let me highlight this before another pen. Okay. Yeah. So this is the Stein star inequality. So P is going to be the stochastic matrix, or just a transition matrix for a Markov chain. For a reversible Markov chain, so pi. Remember, pi is the stationary measure, and we're going to assume reversibility. So pi is a stationary measure. And so before stating the inequality itself, recall that P is a contraction in L2 and more generally in any LP space. So if I take P to the K and apply it to a vector f, or think of it as a function on the state space, and I do compute LP norms, you may want to, I'm writing LP norms, so this little p is different from this capital P, but you can think of little LP equals 2. That's the case I will use today is just this, but in other cases we care about different P's. So before stating the inequality, just recall the standard thing, which says that this is a contraction, so the norm of this is less than the norm of f. And when I write this norm, I mean this is a norm in the space LP of pi. So we're going to apply it all to finite Markov chains. So all this just means you sum, right? So the LP norm to the P is the sum of the Pth powers weighted by pi. So we're working in the space LP of pi, but pi is finitely supported, so everything is elementary. But so what is the inequality is about when you maximize over k, pkf, and so suppose that so let's add the assumption that P is lazy. So remember that Pxx is greater or equal to half. Then when you do this maximization, so again, what does this mean? P to the kf is a function obtained by multiplying, or the vector obtained by multiplying f by P from the left k times. Or you can think of it as a function given the function f. P to the kf is a new function on the state space, which is just P to the kf at the point x is the expectation of f at the point you will get by running the chain for k steps forward. So now that we understand what is P to the kf, so this is, for each k, we can do a max, or in general, a sup over k. Right, so just a pointwise sup for every value. And the inequality is that this is still less than that with a correction factor, which is the adjoint exponent, the conjugate exponent. So remember that 1 over p plus 1 over q equals 1. Right? So here p is something between 1 and infinity, and so is q. The main case today is just little p and little q are both 2. Okay. And this is also the p norm, yes. Thank you. Okay, so
how come the soup is inside of the norm?
that's what makes it, that's what gives it content, right? If it was outside, then it would just follow from this with the, and you wouldn't need this constant. So this is known as a maximal inequality. So we have quantities that we can bound the norm of, but then we are taking a pointwise maximum, right? So p to the kf is, for every k, it's a vector. And look at the, now you can look at a specific entry, like the 7th entry, and for every k, and now take a maximum or a sup over all k's. So this gets, right? If you have a sequence of vectors, and or functions, right? And you just take the sup of these, the pointwise supremum of these functions. For every value, you take a sup, right? So this. No, the sup is over k. That's why I write sup over. So for each x, you take the sup over k of p to the kf at the point x. It's just a sup of a family of functions. Okay, so we're not maximizing each of these functions over x. We're maximizing the family of functions over the parameter k. So I find this inequality quite surprising and impressive. It was proved by Stein in 1961, not with this constant, with a worse constant. Really a very clever, so the paper is just 2 pages, very clever proof combining the Hopf maximal ergodic theorem with the spectral theorem in some clever calculations, and he got an equality like this with a worse dependence on p. It won't matter for us too much, because if you're interested in p equals 2, it doesn't matter. But I emphasize this sharp form found by Starr because we have other applications of this where it's important to let p tend to 1 or infinity. And in those cases, the right dependence really matters. And so Stein proved this in 61. Then Starr in 66, this was his thesis under Giancarlo Rota in MIT. And he proved this. And the paper is about 30 pages, but it turns out it's 30 pages because he had to write a thesis. Really, the core of the argument is a few lines, but it's very, very clever. And if you see this form, you might guess, and that's a correct guess, that this is related to the martingale, to the Dub's maximal inequality for martingales, which has a similar form. However, this is not a martingale. So it's not clear where this is coming from. And so, yes. And, okay, so before really doing the application per se, I want to explain to you where this is coming from, because if you open Starr's paper, it's quite a while. However, we did, in our paper, we did decide to add a half-page appendix just explaining what is needed, because to save people going through the 30 pages. But I want to so the reason this is interesting is, like, where is the martingale in a reversible Markov chain? Well, there are several. We know a bunch of martingales, but this is one I didn't know until looking at this. So instead of proving it for lazy, let's look at, we're going to prove a version without laziness. But we're just going to look at even times. So in fact, a lazy chain observed at all times can be always reduced to a different Markov chain examined only at even times. So
was their result for lazy chains?
Their result was, it's general chains, but for even times.
Oh.
And Okay, in fact, you can easily go from even times to all times just by losing a small constant, but just by losing a factor of 2 in the constant. So let's do this version. So instead of taking sup over all k, we'll take a max over k bounded by capital N. And since the bound on the right doesn't depend on this capital N, then you can, of course, pass to the limit. Okay, now the key thing is what is P2k of f at the point x? So as we said, this is the expectation starting from x of the function f evaluated at x at the Markov chain x at time 2k. And the idea is let's write this as the expectation. So of the expectation f of x2k given xk, right? So we just are using the Tower property of conditional expectations. And let's call this expression Rk. Now, I see I did. Right, so when we, right, so this is Lp of pi. Okay. So now, so this is all fine. Now we're going to take x itself instead of being. Okay. So now we're going to look at. When we compute this norm, it's with respect to Lp of pi. So what this means is that we're really taking this little x and averaging it according to the distribution pi. So the one way we can realize it is just look at the stationary chain. So we're going to take x0 distributed according to pi. And then we run the chain starting at this random point. So now we're going to take P2kf and evaluate it at the random point x0 chosen according to pi. Okay, so now so x0 is now not chosen, not a specific point, but according to pi, and we still have this e pi of Rk, and now we are using. Right, we're fixing this convention that x0 is going to be chosen according to pi. And I claim that when x0 is chosen according to pi, then then Rk is a reverse martingale. That's why it gets the letter R. So remember, x0 is chosen according to pi. I have to emphasize that. And then we look, with that as understanding, we look at the expectation of f of x2k given xk. And now comes the nice trick, because if x0 is distributed according to pi, then so is xk. Now, so xk is a point according to pi, and x2k is just the point obtained by running the chain forward k steps. But the chain is reversible, and if you started at stationarity, run it forward k steps, this has exactly the same distribution as running backward k steps. So this Rk, this is a function of xk. It's measurable with respect to xk, but it's the same function if I look at the expectation f of x0 given xk. All right, and now, right, here we used reversibility. Reversibility means that running the chain forward has the same distribution in running the chain backwards. So this to the law of fx0 given xk is the same as the law of x2k given xk. But now, using the Markov property, conditioning on xk is the same as conditioning on xk, xk plus 1, and so on, the whole future, right? Because given xk, this future is, and x0 are independent. But once we write it in this form, our condition, what does this conditioning mean? It's conditioning on the sigma field generated by this sequence. Right? And this, as k grows, we're conditioning on less and less information. So that's a reverse martingale. You have a decreasing sequence of sigma algebras. You're conditioning on it, and by definition, and you're taking just one fixed random variable, conditioning on decreasing sigma field. That's a reverse martingale. So what does Dub's maximal inequality says? Well, it says that for a martingale, it allows you to bound the maximum of a martingale by the last term. So here we're interested in this. Well, we have to take expectations, but let's look at this quantity. We take max k less than n of rk. So this is a random variable. And we want to bound the LP norm of that. So what Dub tells us is that for a martingale, the LP norm is bounded by q times the norm of the final element for a finite martingale. And here we have a reverse martingale, so we just get the same thing, but the final element of the martingale is the first element of the reverse martingale. So this is what Dub tells us for reverse martingales. But let's look, what is R0? This is Rk. R0 is just f of x0, but that's just our definition. When we write norm f of p, we mean norm within LP of pi, so this is the same thing. Okay, so the LP norm of this is bounded by q norm fp, and then the rest just follows because conditional expectation is a contraction. So once we've bounded the norm of this max, then we have to bound the norm of that max. But this P2kf is just a condition, is just the so I should write this. So e pi of rk, let me rewrite that. A better way to write it is expectation of rk. Okay, maybe, yeah, this notation was actually confusing. Let me erase that. What I should write is the expectation of rk given x0. Because this e pi rk is confusing because that is like that's a number. So this is what I should have written. So so I take P2kf as a function. It's not a constant. And I'm looking at, it's a random variable. And I'm looking at this random variable applied to I'm looking at this function P2kf applied to a random point x0. I'm not averaging that yet. So this is exactly the expectation of rk given x0. And now we just use the fact that the conditional expectation operator is a contraction in LP norm, and conditional expectation of a right, and the maximum of conditional expectations is less than the conditional expectation of the maximum. So you just need two very elementary facts to go from what I checked here to that statement. So it just follows from what we checked here and this conditional expectation. So all this is, so it's really just 3-4 lines, but it's a confusing 3-4 lines, a lot of moving parts. But it's turns out remarkably useful. So besides what I'm going to show in more detail today, we use this with Alex Jai and James Norris to answer a question of David Aldous on Markov chains. Let me quickly tell you this. I won't give you the proof, but I'll just mention this application, which says for random walk on any graph. So I have a simple random walk on a graph of n nodes. I'm taking pt of xy, or pk of xy, max over k and sum over y. So so if I fix a k and I sum p k x y, I just get 1. But suppose I fix in the x, the starting point, I sum over all the points y in the state space, and for each y I ask, what is the maximal probability I'll be at y maximized over time? So I could take a max or a sup here, it doesn't matter. And what David conjectured is that this is, what David Aldous conjectured is that this is bounded by a constant log n, universal constant that doesn't depend on the graph, and the extreme case is a cycle or a path. So if you have a path, here is x, here is y. If the distance here is some number L, then if you look at time k, which is L squared, the probability to go from x to y is going to be about 1 over L. Right? And that's the order of the max. So in this example, when you sum over all these points, you're going to get a sum of 1 over L. So you're going to get a harmonic series, which will give you a log n. So you can't hope to prove anything better. And this is true. So we have it with the constant. We don't have the sharp constant nailed here, but we have it with a very reasonable constant, 4e. And that's in a paper with James Norris and Alex Zhai. And it follows, OK, that's not the only thing in the paper. That's just a lemma in the paper, which follows rather easily from this Stein inequality, which Aldous didn't know, and so I knew about Aldous' conjecture, and trying to prove it by all the other methods I knew completely failed, and even just prove an n to the epsilon here, prove anything better than root n by without using this inequality, I don't know how to do. Okay, so that's a little proselytizing for Starr's inequality. And now I want to continue with the main topic, characterization of cutoff. So I'll remind you of some things we've seen here a lot. So this is the standard notation we've been seeing throughout the week. And thank you. OK, so d of t is this distance in total variation to the stationary distribution. Epsilon mixing times, time until this is less than epsilon. And just t mix is t mix of a quarter. Really fascinating phenomenon. And I'll mention a little of the history later and also later in the week. But just the definition is that a sequence of chains exhibits cutoff if t mix of epsilon asymptotically doesn't depend on epsilon. In other words, t mix epsilon minus t mix of 1 minus epsilon, or you could put here any other number. This is little o of the mixing time. So another way to, and in fact, we're interested in what is the order of this difference. So if we have some sequence Wn, and this inequality holds, C epsilon can depend on epsilon, then we say that Wn is a cutoff window for this chain. In terms of the behavior of the distance to stationarity, a cutoff represents a sharp drop in this distance. So around the point t mix in an interval which is negligible, so the interval of the drop is the window size, you go from total variation distance near 1 to total variation distance near 0. That's what cutoff means. And the width of this interval, again, exactly which interval I'm looking at depends on what height epsilon, but what we want is a window that will work for all epsilon with a suitable constant that depends on epsilon. So the first examples were by Percy and Sashahani. The mixing time for random transpositions is n log n over 2, and the cutoff window is n, and a lot more precise information was obtained. So remember, you pick 2 cards at random, one with your left hand, one with your right hand, swap them. So you might pick the same card. That gets rid of the periodicity. So n log n over 2 is an easy lower bound, because before if you didn't touch all, if you left a lot of cards untouched, your permutation has too many fixed points. We know a random permutation has just one fixed point in expectation, but if you did really less, if you did 0.49 times n log n swaps, then there's a very large number of cards you didn't touch just from coupon collector. And so your permutation has many more fixed points than a random permutation. So the lower bound is easy, the upper bound is not. Anyway, that's the first result, and really a maybe more basic, easier result proved a tiny bit later was that lazy simple random walk on the hypercube, it also has n log n over 2, but somehow for a slightly different reason. So there's still some coupon collector involved. So in lazy walk on the hypercube, we choose a coordinate and randomize it, choose another coordinate and randomize it. So by randomize, I don't mean necessarily flip it, you just replace it by a random bit. So you have n bits. Each time you choose a bit and replace it by a random bit. So to touch all the bits would take you n log n steps, but in the hypercube, you don't need to touch all the bits. If you've touched all the coordinates except for root n, you're already reasonably close to mixed. And if you've touched all of them except for n to the 0.49, then really the measure is indistinguishable from the uniform. The reason is that these n to the 0.49, you don't know where they are. They're in a random locations. And if you take a uniform random vector and then you choose n to the 0.49 random locations and turn those to zeros, that measure is very close in total variation to the uniform measure. Anyway, these are the classical examples. And there's been a lot of progress on Glauber dynamics for the Ising model. I conjectured some time ago that in high temperature this always has cutoff, and this was proved in the lattice in a remarkable series of papers by Lubetsky and Sly. So sorry for abbreviating. So it's Eyal Lubetsky, Alan Sly. Just to see, there are examples without cutoff. If you have random walk on a cycle of n points, and say you do lazy random walk on a cycle, it mixes in order n squared, but there's no specific constant. If you want, in fact, t mix of epsilon is of order n squared times a log of 1 over epsilon. So the closer you want to get, you have to pay by multiplying by a large constant. So there's no cutoff. Now, many chains are believed to exhibit cutoff. Here's the simplest example I know that we don't know, and I guess the best result, and it was obtained here by Ross's students. This is random to random, so you have n cards, you choose a card at random, pull it out, put it back in a random position. Okay, so it's order n log n of these moves are needed, but the exact constant is not known. Conjectured to be, Percy conjectured 3/4, and that's now. So who is the student?
Eliran Subad.
Right, Eliran proved a lower bound of 3/4 n log n. We still don't know that as an upper bound. But most of the studies of cutoff so far have been focusing on examples, special classes of examples, either with special structure, a lot of symmetry as you have in groups. Ising model is a fascinating class. And this paper is part of an attempt to make kind of a more general theory. And we have something, but there's still much more to do. So in 2004, in a workshop that in the workshop on mixing at AIM in Palo Alto, I suggested that in many cases, this will be the criterion for cutoff. The spectral gap times the mixing time should go to infinity. It's easy to show this is a necessary condition. So if the spectral gap times the mixing time isn't going to infinity, you're not going to get cutoff. And so, for instance, in the cycle, the spectral gap is order 1 over n squared. The mixing time is n squared, and there's no cutoff. However, even before that workshop, when I discussed this with David Aldous, he pointed out that this can't be true in complete generality. So there are examples where this condition holds, but there's no cutoff. And Igor Pak gave another example. So this says, well, if we believe that the product condition is still very relevant, we know it's necessary, we need additional side conditions to ensure cutoff. But the idea is, most proofs of cutoff by now require extremely fine understanding of the chain, either using representation theory or explicit diagonalization, or in the case of Lubetsky and Sly, really very refined analysis of the Ising model. And we'd like to be able to conclude that the chain has cutoff by kind of more rough considerations. So it's usually easier to control the mixing time up to a constant than it is to find the constant. So if a condition like this would be sufficient, we'd be very happy, because we just need to estimate the spectral gap and the mixing time up to constants in order to know whether this condition holds. Unfortunately, this isn't enough, but that's the goal. So here is the Aldous example, or some variant of the Aldous example. So you have, so in this part of the graph, you're just walking to the right. So you walk to the right with probability 1/6, to the left with probability 1 over 12, and mostly you stay in place. Anyway, so you still zoom to the right with a positive speed, I guess, and it will take you on average 120 n to go from this point to this. This part, the important part then starts. When you reach this point, you either can travel on this upper part or on the lower part. And both of these, you have a drift to the right, but the drift is stronger on the top than it is, the drift is stronger on the bottom than it is at the top. So here the drift is 1/6, and here the drift is 1 over 12. So if you go on the bottom, you'll reach this in another 6n steps, you'll reach to the right. And if you go on the top, you'll reach it in about 12n additional steps. Now, really reaching this right-hand point is the signature of mixing, because the way this chain is defined, it is reversible, and the stationary distribution grows exponentially as you move to the right. So if you look at the neighborhood, a small neighborhood of this vertex y, it contains almost all the stationary measure. So it's easy to show that mixing here is essentially equivalent to reaching y. But there are these two routes you could reach y. Once you're here, you might dawdle a little bit, but eventually you'll just decide, the particle will decide, is it going here or here, because there's a drift pulling it. And that's going to determine the time it reaches y. And from this, it's not hard to see that the profile of the distance to stationarity, it's near 1 until the first chance you have to reach the right is after time 126n. And at that time, you have a drop in the distance to stationarity. But still, there's a possibility that, so this drop corresponds to if you moved on the fast highway on the bottom. But there's still a possibility that you're moving here, and until the part of the mass corresponds to moving on the top can reach y, you don't mix. So you have a second drop at time 132n. Okay, of course, these parameters are somewhat arbitrary, but I hope you get the idea. And why is this? So this graph, this is actually a weighted expander. So you can check that for any set, its weighted boundary is at least a constant times its volume for any set of volume at most a half. So the spectral gap here turns out to be order 1. But of course, the mixing time is order n. So we see that the product condition holds, yet there is no cutoff. So I gave this example in such detail because this illustrates one of the enemies we have in trying to establish the product condition implies cutoff. Well, it doesn't because of, well, among other things, this possibility. So what goes wrong here is there's the vertex y or its neighborhood is a very large set, and we could hit this set in two ways that take very different times. So this suggests a connection between cutoff and concentration of hitting times, and this will connect to the talk Perla gave earlier in the week, where she explained the connection of mixing time and hitting time at the order of a constant. So we know that the mixing time up to constant is equivalent to the maximum over all large sets of the hitting time of that set. So I'm just going to skip here. So recall the theorem that Perla explained is that the mixing time up to constant is this TH, where TH is the maximum over all sets of measure at least a half of the hitting time of the set. Okay, she explained it with 1/8 here, but it's true with any threshold here, which is at most a half. And as she also told you why the threshold a half can't be improved in general here. Okay, so this is an equivalent up to constant, and here we'd like to sharpen it. So this is in the work with Hermon and Basu, where we'd like to sharpen it and show under the product condition this estimate up to constants can be replaced by ratio tending to 1. So one kind of prototype case that's motivated this, partly motivated this work is the case of birth and death chains. So you have a path of length n, and the birth and death chain is just a Markov chain where you can either stay in place or go one to the right or one to the left. To avoid periodicity, let's think of lazy chains. One could also think of continuous time chains. So in that setup, Percy with Laurent Salov-Coste showed that separation cutoff is equivalent to the product condition, and Perla explained separation distance in her talk. I won't need it today, so I won't discuss it. But then there was the analogous theorem for total variation cutoff, which is the one we're most interested in. We proved with Jian Ding and Eyal Lubetsky a few years later. So a sequence of birth and death chains. So if we have just walking on a line, there we have cutoff exactly when the product condition holds. The mixing time multiplied by the spectral gap goes to infinity. Ross, when did we start? Well, how long do I have?
I failed to.
Okay.
Start on time. But you have. Let's see, 1 second.
Yeah.
I would say it was in the 10:45.
Okay. Thank you. So, so in both of these papers, the proof were based on really properties of hitting times in birth and death chains, and a beautiful theorem of Carlin and McGregor that says the hitting time in such a chain from one vertex to another vertex can be written as a sum of independent geometric variables. So this is not at all an obvious representation. It's not, right? So if I want to go from one point to another point in a line, I could say, well, I want to go from 0 to 1, from 1 to 2, from 2 to 3. These hitting times are all independent, but they're not geometric, and they have fat tails. So there is they could have fat tails. So there is a different representation more useful, or sometimes more useful, found by Carlin and McGregor. And this was a key element in both of these papers. And it's very special to birth and death chains. So the methods in those papers don't even work if our chain is a walk on a path which could jump 0, ±1, or ±2 with some probabilities. So you can walk not just to the neighbors, but also to the neighbors of the neighbors. This breaks down the proofs in both these papers. However, now we know the product condition is sharp for cutoff in such chains and many more. So if you have any chain on a path or that jumps bounded distances and and has positive probability of jumping plus minus 1 and jumps bounded distances, or even a chain, if your underlying graph is a tree structure and you're allowed to jump a bounded distance on the tree, then in these chains also the product condition is sharp for cutoff. So observe that what was crucial in the Alice example is we had very large girth. We had two different ways to reach target y, which kind of got disconnected early on, and we had a very large cycle. So if we ensure no large cycles, then the product condition is sharp. And here is one statement. Say we have a, so here I'm stating it for nearest neighbor walk on a tree. So we have any tree and any weights on the edges, then the t mix of epsilon minus t mix of 1 minus epsilon can be bounded this way. So the key thing is what you have here is the geometric mean of the relaxation time, which is the inverse gap, and the mixing time. So in particular, if the mixing time, if we have a sequence of chains and this product condition holds, that means that the relaxation time is negligible to the mixing time. Then this geometric mean is itself negligible compared to the mixing time, so we have cutoff. So we have, if the product condition holds, we have cutoff with this window, which is the geometric mean of the relaxation and the mixing. And already in the case of birth and death chains, you cannot put, in general, a lower window. So we have examples where the window is of this size. And this, even for the case of birth and death chains, this improves the result in the earlier papers in terms of the dependence on epsilon. So the key to this proof, which I won't be able to give you, all the details, but I want to give some idea and relate it to this Stein-Star inequality. So we're still going to relate mixing to hitting time of large sets, as Perla did in her talk. But instead of looking at the expected hitting time, we're going to look at the tails of the hitting times. So just like we have t mix of epsilon determines what is the time that we're close in total variation, hit of epsilon will say what's the first time, so that for any large set, so any set of measure at least a half, the probability you have not hit it yet should be less than epsilon. Okay, is that clear? So this is an analog of the t-mix parameter. It's the tail of hitting times for the worst set and the worst starting point. And a key, general theorem is that, okay, cutoff is equivalent to cutoff of hitting times. So we say that a sequence of chains has a hitting cutoff if hit n epsilon minus hit n1 minus epsilon is negligible to, say, the hitting time for with epsilon equals 1/4. And one result we have abstract. So I said, one goal is to make a theory of cutoff, not just this or that class of examples. And so this is progress in that direction, saying that cutoff is equivalent to hitting cutoff. So, and in fact, both of these conditions imply the product condition. So initially we stated it as cutoff is equivalent to product and hit cutoff, but in fact, each of these implies the product condition. So really, cutoff is equivalent to concentration of hitting times of the sets that are hardest to hit. And for trees, we use this because hitting cutoff is easier to understand in trees. What makes this hard in general is the definition of hit epsilon involves a quantifier over all sets. So you have to understand what are the sets that are hardest to hit. In a tree, it's easy to guess and possible to prove that the hardest sets are the sets that are hiding behind the central vertex. I'll explain this later, and I think Perla will give another application of these central vertices later in the week. Okay, so let me, this is the abstract result, but it, always behind every, yes?
On your previous slide, when you had for trees, you didn't have reversibility.
Yes, so the previous result was a chain which is restricted to walk on the edges of the tree. So those are always reversible. Right? So in the previous, let me go back. So when we say a Markov chain on a tree, what I mean there, I said it in words, but I didn't emphasize enough. I mean, in this statement, I'm assuming that the chain is only walking along the edges. Every step is along an edge of the tree. That forces reversibility. Okay, so behind any abstract theorem, there is some more useful inequality. And this is the inequality here. So actually, we need several inequalities for the abstract theorem. This is a key one that I want to emphasize. So T mix of 2 epsilon, it can be compared to 2 hitting times with an error or perturbation term which is of the order of the relaxation time. Okay? So recall Perla's lecture where the mixing time was shown to be equivalent to a hitting time, but up to constant factors. The idea is here, there's no hidden constants here. Everything is spelled out. So there is no, so really T mix, and here we have hit epsilon with constant 1 in front, and hit 3 epsilon with constant 1 in front. And, well, the only issue is we have these correction terms which are of the order of the relaxation time. But under the product condition, if we want to think of that case, because the product condition, if you're going to work on establishing cutoff, if you can't establish the product condition, you might as well go home, because the product condition is much rougher to decide. You just have to estimate things up to constant. So we have a chain. We want to study cutoff. Maybe the first order of business, check if the product condition holds. If it doesn't, there's no cutoff. If it does, well, then the real work starts. And so assume that the product condition holds. Then this says that T mix epsilon is equivalent up to a negligible error to hitting times. Well, the upper bound involves epsilon here. The lower bound involves hit 3 epsilon. But you see that if you have concentration of the hitting times, if hit epsilon doesn't depend much on epsilon, then T mix doesn't depend much on epsilon. What I'm hiding here, this controls well the behavior when epsilon is near 0. For cutoff, we actually need to also understand the behavior when the total variation distance is near 1. And we also have that with a related series of inequalities, but I won't get into that. So there's 2 directions here. The easy direction, which again is, so this proof was very much modeled after the proof in the work with Perla, but in a different setting. So there's one direction which is if in order to mix, the chain must escape from small sets. So this is, in this inequality, it's always easier to bound hitting times from above by mixing times, and harder to go the other way. Okay, so maybe I'll skip the easy direction, and I want to focus on the harder direction, the more interesting one, which is to bound the mixing time from above by the hitting time. Again, by the way, this paper is available in full detail on the archive if you want to see more. So I'm going to emphasize what I think is the key element, which is the upper bound on mixing time in terms of hitting. So we want to control the distance in total variation between the chain and the stationary distribution. So, right, so what does it mean the chain is epsilon mix? It means, so let's focus on a particular set A. It means that this difference is less than epsilon. And we're going to get this epsilon mixing by finding a suitable certificate. So we're going to find a very large set G, so that if we hit G by time little t, then we're very likely to be mixed by time t plus s. And all that with respect to a set A. So for every set A, we're going to attach a certain set G. So hitting G by time t will serve as a certificate of being epsilon mixed at time t plus s with respect to A. So here is so I'm going to show in this talk just really one calculation. This is it. So we're going to write t for the parameter hit epsilon, and s for the relaxation time scaled by a log 2 over epsilon. And then the key inequality I stated before can just be written as t mix of 2 epsilon is bounded by t plus s. Okay, that's what we want to show. We want to bound mixing time from above by this hitting parameter plus a relaxation parameter. Okay, so this is a statement involving total variation distance on all sets A. So think of a set A. For every set A, we're going to find a set G, which will be a certificate of mixing in A, and this is a set G. So G is all points little g, with the property that if you start at little g and you run the chain for time s tilde, you're going to be close to the stationary distribution. Now, I want to separate what's the standard and what's the non-standard thing here. If instead of s tilde here, I would put s. I want pgs of a minus pi a to be less than this parameter, e to the minus s over TRL. Then this is completely standard spectral analysis. If instead of this, if here instead of s tilde, I would have s. So it just follows from the writing out the spectral representation of the transition matrix P, and very standard calculation. Okay? I won't write it out. What's non-standard is the fact that I have a quantifier here that I want this inequality to hold simultaneously for all s tilde bigger than s. That's sort of the novel feature which relates to stars inequality. So again, if I just had an s here, then the fact that this G is a very large set would be standard. But it's also true when we have the s tilde, and that's a consequence of stars inequality. Okay, so you see that, so this is just a matter of rewriting the notation to infer this from star. And you get that I've chose the parameter so that star will tell us that the probability of this is at least a half. And if you believe that for a moment, okay, so this is just a consequence of stars inequality, then we know by the definition of t, which is hit epsilon, we know that the probability we fail to hit this set G by time t is at most epsilon. That's the definition of this hit epsilon. Finally, for any x, any starting point x, any set A, I want to check what is the distance in total variation. So I want to check what's the probability of being in A in time t plus s, compare that to pi of A. So this difference, I separated into two pieces. One piece comes from the event that Tg was bigger than t. This probability is going to be less than epsilon, as we mentioned here, by the definition of hit epsilon, and since G is a big set. And then what we have left, so this is the case when we haven't hit G by time t. In the remaining part of the probability space, we have hit G by time t, but I don't know exactly when, sometime before t. And now I'm interested in distribution in time t plus s. Well, from the hitting time until time t plus s, how much time is left? Not exactly s, I don't know, but it's some number which is at least s. And here is where this max star maximal inequality comes to the rescue, that because I can put here, this is the maximum over all g and g. So I look at the time and place where I hit g. This is some time less than t, and some place little g. And the time remaining until t plus s is some number s tilde. And so all I need to control is this difference, pg s tilde a minus pi of a. And this difference is also less than epsilon, just by the definition of capital G. But I have to be able to plug in this maximum. If I just know it for a fixed time, it's not good enough. OK, so again, this is an elementary deduction. The fact that pi g greater equal half is an elementary deduction from star. You're just using Markov's inequality. I won't spell it out due to time, but it's really really easy from star. OK, so let me right, so this is, again, saying what star is, as I wrote there. OK, maybe I'll say a few words how we get the inequality we use from star. So we're going to take p equals 2 and look at the function fs, which is the indicator of a, subtract its mean, and run the chain forward for s steps. So this gives us some function fs. And g complement, so the set g as we defined it, its complement is, if you plug in the definitions, it's just contained in the set where fs star squared is bigger than 8 times the norm of fs squared. And once you have it in this form, then you can bound the probability of g complement using Markov's inequality. Because you know the norm of fs star squared, the integral of fs star squared is at most 4 times the norm of fs squared. So because we have the 8 here, we get the half. So tree structure can be used to determine the identity of the worst sets to hit. And OK, so a central vertex, let's see. A vertex is called central, and this will, this is, again, used in several different places. A vertex is called central if when you remove it from a tree, the resulting components are all less than half the volume of the tree. Say we use pi to compute volume. Okay, so there always is a central vertex, and there are always at most 2. This is a nice combinatorics exercise. And if we have a central vertex and we have a starting point, then there's always a set hiding behind the central vertex with respect to that starting point. So if I start from x, I look at the central vertex. There are the set A of points I can't reach without passing through the central vertex. And this set has measure at least a half, because my component has measure at most a half. And these sets are the hardest sets to hit in a tree. So that's what distinguishes trees. In general spaces, it's hard to say what are the sets that are hardest to hit. But in a tree, we can understand it and hence complete the analysis of cutoff. So I'm going to skip most of the rest. And as I mentioned previously, the birth and death case, which was analyzed, was very sensitive because it used precise representations of hitting times. Now we have kind of a more robust criteria, so we can work with chains that on a segment that jump a larger distance. There's still a lot of open problems. So we've swapped understanding cutoff for understanding concentration of hitting times, which is sometimes easier, but certainly not always. So most of the work is still ahead. Thanks for your attention.